Hello everyone, welcome to the another video. Let's solve furthermore linear algebra question that are asked in the GATE exam. So now let's start with the question number 1. Here, question number 1 asking about the eigenvector of this 2 cross 2 matrix. So now again we have to use the same concept regarding the eigenvector. If I am multiplying a matrix A with any general vector x, and if in the output I am getting this the same vector which is x but multiplied with some scalar, then I can say here this x is the eigenvector of this matrix A, and here the value of lambda is known as the eigenvalue for any particular matrix. So now here we have given the matrix A and they are asking about this vector x. So now we can solve by the conventional method, finding the characteristic equation of this matrix and solving and to get the value of lambda, and for any particular lambda we get one particular vector. But now here in this MCQ type question we directly have to go from this option. So let's go one by one from this four option. So now let's start with the option A. So I have to put the matrix A here. A has entry -5, 2, -9 and 6, and I have to multiply this matrix with the vector given in the option A. So now let's do the multiplication. So here -5 multiply with -1, so +1 +2, so 7. Now here 9 plus 6, so I'm getting 15. So now let's try to find out some scalar to represent this vector in this lambda time initial one. The initial one has value -1 and 1. So now you can easily say that we are not getting any such scalar to represent this vector in this form. So we put here not equal to. So now option A does not contain the correct eigenvector for this matrix. So now let's move to the next option. Again let's put the matrix as it is: -5, 2, -9, 6. Now let's multiply it with vector given in the option B. So now here -5 plus 2, so -3, and here -9 plus 6, again I am getting -3. So now you can easily see that we can take out -3 from this vector and we are getting the initial one. So let's write it in this way: -3 times the this 1 1 vector, and which is the initial one. So we have represented this vector in this lambda time x, and here the value of lambda is -3. So we can say lambda here is -3. So now in nutshell we can say that the vector B, option B contains the correct eigenvector for this 2 cross 2 matrix, because vector given in the option B is satisfying this condition. So vector B contains the correct eigenvector for this matrix. Now for the more clarity you can also go through the option C and D. Let's quickly do it. It will not satisfy this condition. So now let's do the multiplication. So here 20 plus 18, so 38. Sorry, here top we have 5 multiply with minus, so sorry, we are getting 10, 10 plus 18, so 28. Now here 18 plus 6 multiply with 9, 51. So now let's again further add these two numbers. So here we are getting 69. So now again you can see that we cannot represent this vector 28 comma 69 in this -2 comma 9 multiplied with some scalar lambda. So again we cannot represent this vector in this form. So now here again we have to put not equal to. So now option C is also wrong. Now in the same way you can say for the option D. Let's do the multiplication. So minus 10, minus 2, minus 12, here minus 18 and minus 6, so minus 23. So now again we are not getting any such scalar to represent this vector in this lambda times the initial vector. So again we have to put not equal to. Sorry for mistake, here we are getting minus 24, not minus 23. Now we cannot represent this vector again in this form. So again we have to put not equal to here. So now you can see option D is also not satisfying this condition. So only correct eigenvector for this matrix is given in the option B. Now let's move to the question number 2. Okay, now question 2 says which one of the following equation is identifying for arbitrary 3 cross 3 real matrices P, Q and R. Okay, here it is given that these three matrices P, Q and R are real and the dimension is 3 cross 3. So now first equation is given in the option A. Option A says if we are multiplying this P with this bracket, then it equal to, we can multiply this P with this Q here. So here on the right hand side they have written P multiplied with Q. Yes, we are multiplying this bracket with P from the left hand side. So we have to put P here and Q here in the same order. So now again this P will multiply with this R also. But now here in the right hand side they have flipped the R and P. They have written R plus and P later. So now so we can say these are not, this left hand side and right hand side not equal, because here the order is reversed. Instead of RP, if we have PR, then the equality hold, but here the equality does not hold. So now option A does not contain the correct statement. So now let's move to the option B. Option B says the determinant of these two individual after summation is equal to the individual determinant, and we have to edit them. But now here we have equation in the multiplication form. If I have it, I have to find the determinant of this multiplication of these two vectors. Then I can write it is equal to the individual determinant, and I have to just multiply it together like this. But now here in this plus, in this case A plus Q, we do not have any equation like this. So option B is also not correct one. Now option C says if we square the subtraction of these two matrix, then in the, if we expand this equation, then we are getting this. So now first of all let's do it here. So I can write like this, PQ, again P minus Q, because here the power is 2, so I can multiply this bracket with itself. So now let's do the multiplication one by one. So here this P, here remember this P, Q, R are the matrices, not any scalar. Now here P with P, so I get P multiplied with P, and this again this P multiplied with this Q, so minus PQ. Now again this minus Q multiplied with plus P, so again minus QP, and now finally this minus Q multiplied with this minus Q, so minus minus plus, and Q multiplied with Q. Now remember what we are calling, if the matrix multiplying with itself, we are saying as P square. Now here this PQ remain as it is, minus QP is also remain as it is, and plus Q square, because here this PQ and Q are not equal to, that is the case in the this matrix. But now if instead of this PQR matrices, if they are real number, then this PQ and QR multiplication are equal, then they are add together and form this equation. But here this PQ and QR are this multiplication, P times Q and Q times P are not equal, because here they are matrices. So now we can also say option C is also not correct because they have added these two here, these two term, but we cannot say that these two terms are always equal. It happen maybe sometime, but not always. It depend on this matrix. But now here any condition about this PQ are not given, then this condition is not true. So now let's last option D, and which is of course correct because all the threes are wrong. Sorry, A B C D, all threes are wrong statement, then D must be correct. So now again let's write it here, P plus Q again times P plus Q, because here also they have squared this whole term. So now again let's do the same procedure. Here I am getting P square plus PQ plus QP plus Q square. Now look at the option D. They haven't added these two terms and make 2 times QP, but they put it as it is, that we are getting from here. So now we can say the option D is the always correct statement about any three matrices PQR. So now option D is the correct answer. Let's move to the next question. Okay, now let's solve question number 3. Question 3 says consider a 3 cross 3 real symmetric matrix S such that two of its eigenvalues are A, and here A does not equal to 0, and B also has non-zero values with respective eigenvector. Okay, we have also given these two eigenvalue. So let's assume we have lambda 1 and lambda 2 is an eigenvalue, and here eigenvalue are given A and B, and one condition is given that A is not equal to 0 and B is also not equal to 0. That's mean this eigenvalue are non-zero, and we also have given the eigenvector. Let's write here, call it x1 and x2. These two are eigenvector. Okay, now if now the further condition is given about the value of A and B, it is also given that these both eigenvalue are not equal. So we can say this lambda 1 is not equal to lambda 2. Okay, we have three condition given like this. So they are asking about this x1 time y1 plus x2 time y2 plus x3 time y3. In fact, they are asking about the dot product of these two. If you take the dot product, so this first element will multiply with this one, plus this second multiply with this one, plus this third multiply with this one. So in terms we are getting this equation after the taking the dot product of these two vector, and which are here eigenvectors. So now here for any symmetric matrix, it has one property. Let's write it here. For real for real symmetrics, for two distinct eigenvector corresponding to two distinct eigenvalue. Here in this case eigenvalues are A and B and they are distinct. It is given in the question in this form. Then two eigenvector two eigenvector are orthogonal to each other. So now it is the property for a real symmetric matrix. And now the if two vectors are orthogonal, let's call v1 and v2. and v2, then we know that the dot product between these two product must give 0, then and then they are orthogonal. So now same way, if we take the dot product of these two vector here, the eigenvector are given in this form x1, x2, x3 and y1, y2, y3. So let's write it here x1, x2 and x3. I have to take the dot product it with the second vector eigenvector. So it has value y1, y2 and y3. So now let's take the dot product. So here x1 y1 plus x2 y2 plus x3 y3, and now here from the property we know that the two eigenvectors corresponding to two distinct eigenvalue for any real symmetric matrix are orthogonal. Then we equate this dot product equal to 0. So now that is what they are asking in this form. So it's equal to 0. So option D contains the correct answer. So now let's move to the question number 4. Okay, question 4 says given that the determinant of a matrix is minus 12, determinant of the matrix is what? Okay, now here we have given the value of this determinant and they are asking about the determinant of this matrix. We can easily find by expanding with any row and column for this 3 cross 3 matrix, because here we are only getting 6 term in the expansion because we have a 3 cross 3 matrix, so it is easier. But now here first think about this. If the condition is given like this, then there is a pretty good chance that this matrix has some relation with this one. So now let's first of all look at the entries of this matrix. So now you can see this row, first row is just twice as much as this first one in the this vector, this matrix. Now again look at the second row. This row is also twice as large as this one, because here we have 2, so here we have 4, here we have 6, so here we have 12 and here we have 4, so here entry is 8. So again this row is 2 times this second row in this matrix. So now again let's look at this third row, which is last one. So again the values are in this matrix are twice as large as given in this one. So now this third row is also multiplied with 2. So now what I am going to do is just simply the take out the 2 from this first row, and also factor 2 from the second row and factor 2 from this third row. And what I am getting here, let's first of all make this. I am replacing this matrix notation with determinant because I have to find the determinant. So I can replace this one with, sorry, this 2 with 1 because 2 is common out. Now here I have to write 3 and 0, and I have to put 2 here. Now again the same thing with this second row. Again let's multiply this 2 with 2 because 2 will also, this 2 factor will come out from this second row. So here I am getting 2, 6 and 4, and add also one more 2 from this third row. So let's multiply this terms with again 2, and here I am getting minus 1, 0 and 2. So now this is the constant term, and now we have to just only take the determinant of the remaining, and it is given in the question. So now we just simply put this determinant equal to minus 12. So here we are getting 2 times 3 multiplied with minus 12. So here this value will be 8, 2 cube will be 8, and we have to multiply it with minus 12. So we are getting minus 96. So now we can say option B contain the correct determinant for this matrix. You can easily get this number by just expanding this determinant about this first row or any other row or column you like. Now let's move to the next question. Okay, question 5 says choose the correct set of functions which are linearly dependent. Okay, so they are asking about the correct set of functions which are linearly dependent. So now first of all, what does this mean, linearly dependent? So now if I am I am able to represent one function, let's call it h of x in this form, like here in some constant c1 times some function x of x plus another function c2 times g of x. Now here this c1 and c2 are constant. C1 and C2 are real constant. So now you can see these two functions f of x and g of x, if they are added in some particular manner after multiplying this constant, then I am getting the third function. So now I can say this third function s of x is generally combination of these two functions. So I can say this s of x is linearly dependent on this function. So if I have these two functions, then I am also automatically get this third one. So there is in specific manner I have just two functions, these which are f of x and g of x, because here the h of x is just simply the some particular combination of these two functions. So I can say this function are linearly dependent. Okay, so now here the function are given in this trigonometric form, so we have to need some trigonometric formula. So now the let's look at the option a. Option a says the option a given have three function. One is sine of x, other is sine square x, and other is uh, cos square x. So now let's try to relate these three functions. So now we have equation in the trigonometry identity equation, sine square x plus cos square x equal to 1. So now we do not have any linear equation to represent these three function in this form. So now we can easily say that option A contain the linearly independent set of function. So now let's move to the option B. Option B has a three function, cos of x, sine of x, and tan of x. So we know the relationship between these three functions. So I can write tan of x equal to sine of x divided by cos of x. So I cannot represent this tan of x in the linear combination of these remaining two functions, which are sine of x and cos of x. So again there is a relation, but they are not in the linear form. So again these three functions are not linearly, we have to find the linearly dependent function. So again option B is wrong. Now let's move to the option C. Option C has a three function which are cos 2x, sin square x, and cos square x. Now again, if you remember the formula of this cos 2x, so let's write it here. Cos 2x equal to cos square x minus sin square x. It is an half angle formula because the angle is reduced here by half. Here angle is 2x, so here angle on the right hand side is just simply x, so half angle. So now this is the relation. So now just simply compare this function with this one above condition I have written. So now here the h of x is cos 2x, and here the constant c1 has value here in this particular case as 1, and the value of c2 here is minus 1, and the here in this place f of x we have function cos square x, and in the place of g of x we have function sin square x. So we have combined these two function and we are getting the third one. So we can say this third one is actually linearly dependent on these two function. So we can say the option C contain the correct set of function which are linearly dependent. So option C is the correct set of function. So now let's also check option D. Option D has three function cos 2x, sin x, and cos x. Again, if here they haven't square it, so again we cannot linearly relate these three function. So again we are saying not equal to. Now if someone does not remember this formula, so what to do? So we have need some general procedure, and if there are other function like exponential and logarithmics, and the simple relation we do not form easily. So what we have to do, we have to just form the Wronskian. We have to form Wronskian, and what is that? First of all we have to make the determinant like this, and here let's assume we have a three function. So we are getting a Wronskian of the dimension 3 cross 3. Simply Wronskian is nothing but the determinant formed by some specific step. So I have to write the function, first function. Let's call first function is f of x. the second function is g of x, and the third function is h of x. And in the next row, what I have to do is just simply first time differentiate this function with respect to x. So I am denoting as f dash of x. Same way, g dash of x and h dash of x. Now in the last row, I have to further differentiate this function. So I am getting second derivative of this function. Again here, second derivative, and here also s double prime x. And now after that, I have to find the determinant, and I am getting some function in, let's call it p of x, because after, if you find the determinant, then you are get some function in this variable x form, because here variable everywhere is x. So now if for any particular value of x, or in general if this function p of x is just simply a 0, then, then we can say these three functions f of x, g of x and h of x are linearly dependent. This means LD in short form, linearly dependent. So now if the second condition is that if this p of x is not equal to 0 for any value of x, so we can say these three functions are linearly independent for x belongs to any real number. So now according to this condition of this p of x, after the finding the determinant of this Wronskian matrix, we can say about the dependency of this function. If the Wronskian is 0, then we can say that the function are linearly dependent. If the Wronskian is non-zero, then we can say the function are independent, linearly independent. But now here the Wronskian may have any order depending on the number of function. It may have 4 cross 4 order or 5 cross 5. So according to that, we have to go up to the derivative. Now here we have three function, so we have to go to a second order derivative. In the general way, if I have n function, then I have to go n minus 1th derivative, because one derivative is less than the number of function I have. So now in this way you can easily check the linearly dependency of any general function. So now let's move to the next question. Okay, now let's solve question number 6. Question 6 asking if A, we have given a matrix A, then the determinant of if its inverse correct to the two decimal place. Okay, so they are asking about the determinant of inverse. So now here one may can find the inverse first. So I have to use the function of formula of inverse matrix, which look like that. I have to multiply it with adjoint of matrix A, and now here this notation is denote the determinant of this matrix, not mod sign here A about this A, because here A is not any scalar, here A is matrix. So here this vertical line are denote the determinant. So now but here they are asking about the determinant. So just simply we can use one property, that the determinant of A inverse, it is just simply 1 upon determinant of A, or in the other word the inverse value of the determinant of this original matrix A. So just what I have to do is just to find the determinant of A here, and I have to take the inverse of that number, so I can easily get the value of determinant of this inverse matrix. So now let's find the determinant of this original matrix. And now here you can also look at the matrix A, and you can recall it is nothing but the triangular matrix, because all the entries below this diagonal are 0. You can see these three entries below, which are below the this diagonal are 0. So we can say it is an upper triangular matrix, and upper triangular matrix has one important property. If we have any upper triangular matrix, then simply just any triangular, either it may be upper triangular or lower triangular, and the determinant of this particular matrix is just simply the multiplication of its all diagonal value. So here I can write here the determinant of A here in this case is just simply the multiplication of this four number which are present at this diagonal place. So I am getting the determinant as 4, and I have to take the inverse of this 4 to find the determinant of inverse. So I can say determinant of this inverse matrix is just simply 1 divided 4, and which is 0.25. So I have to write here 0.25. 2 5. Okay, now let's move to the next question. Okay, now question 7 says which one of the following matrices are is singular. Sorry, here matrix not which one of the following matrix is singular. So now here, first of all, what is what does it means to be singular? So if I am getting the determinant of any general matrix A as 0, then I can say matrix matrix A is singular. If the determinant of any general matrix is 0, then the matrix is singular. In the other way, if the determinant is has non-zero value, then matrix is non-singular. Now here is the trick to remember. Here maybe some students are confused about this singular and non-singular according to this value of determinant either 0 or not equal to. Here for the not equal to we have to write non first in the front of singular. If the non is there, then we have to put not equal to, and if only the singular is there, then we have to put equal to. Focus on this non word here. If the matrix is non-singular, then the determinant is not equal to 0. We have to put here not equal to, because here the term is non, and here if only the term is singular, then we have to put equal to 0. So now simply we have to what we have to do is just simply find the determinant, and here the matrix are all the matrices are in 2 cross 2 order. Sorry, here follow. Okay, I think it is right here. Let's forget about it. Here we have to find the determinant. Simply just we have to multiply these two number, and we have to subtract the multiplication of these two. So here let's check for option A. So I can say 6 minus 5 and equal to I am getting is 1. So again here is not equal to 0. So matrix is non-singular. Now let's check for the option B. So 8 minus. So again we are getting minus 10. Again not here I am getting value non-zero. So again I have to put here not. Now let's move to the option C. So here I am getting 6 multiplied with 2, so 12 minus 3 multiplied with 4 minus 12 again equal to 0. So now I am getting equal to 0. So I have to put here singular, because I am getting the 0 value. So option C contain the singular matrix. So now also quickly check for the option D. So here 9 minus 4, which is 5, again non-zero value, so non-singular. So now option C is the correct one. Let's move to the next question. Okay, now let's solve question 8. Question 8 says the matrix has, okay, they're asking about the eigenvalue and eigenvector. So option A has given the statement complex eigenvalue but real eigenvector. Option B says the real eigenvalue and eigenvector. Option C says a real eigenvalue and complex eigenvector. Option D says a complex eigenvalue and complex eigenvector. For checking these three four statement, we first of all have to find the eigenvalue and eigenvector of this matrix, and then we can say about the eigenvalue and eigenvector. So first of all, I have to form the characteristic equation using this condition to find the eigenvalue here. So now here A is given. A is just simply this matrix, and I have to subtract the lambda time the identity matrix. Here identity matrix is also order 2 because A has order 2. So let's directly form the determinant. 2 minus lambda, here minus 4, 4 minus 2 minus lambda, and I have to find determinant and equate equal to 0. So now let's if I multiply these two, so here 2 minus lambda multiply with minus 2 minus lambda, and here minus multiplication of these two, so minus 16, so minus minus will be plus 60 equal to 0. So now let's do multiply this two bracket. So here minus 4 minus 2 lambda plus 2 lambda and plus lambda square and plus 16 is already there. So now I can cancel these two term, and here I am getting lambda square plus 12 equal to 0. So now let's solve for lambda. So lambda square equal to minus 12. So I can say lambda has eigenvalues are complex because this square has a negative value. So I can write here like this, plus and minus I times under root of 12. So now we are sure about the eigenvalue. The eigenvalues are complex. So now let's look at the option again. Option says real eigenvalue. No, option B is not correct one because we are getting the complex eigenvalue. Again, option C says real eigenvalue. Option C is also not correct one. Now the remaining two options A and B both are saying the complex eigenvalue. But for to choose the correct from these two, we have to also find the eigenvector because the second condition is about the eigenvector. So now first let's how to find the eigenvector. Just simply what we have to do. Let's I have matrix A and I am multiplying with vector x. It's this basic definition of this concept of eigenvector from the concept of eigenvector. So let's bring this right hand side on the left hand side. So here minus lambda x equal to 0. But now here 0 is the vector because on the left hand side we have also vector. So let's take this x common. So now I can write this a minus lambda I multiplied with x equal to 0. Now here I have find out the value of this lambda and I need the vector x here. So let first of all choose lambda plus under root of 12 multiplied with I. So if I am taking this lambda, then from this 2 I have to subtract this value. So I can write 2 minus I times under root of 12. This minus 4 will remain as it is. Now in the second row, this 4 will remain as it is. I have to also subtract this number from this fourth entry. Sorry, here it is matrix. And now let's assume this vector has two value in general term, x1 and x2, and here these are unknown. And on the right hand side, we have equal to 0. So now what all we have to do is just we have to solve for this unknown in which are present in this form x1 and x2. So now let's multiply these two terms, these two matrices on the left hand side. So here what we are getting is just simply this 2 minus I multiplied with under root of 12 times x1 minus 4x2. Now in the second row I am getting 4 times x1 plus minus 2 minus I under root of 12 times x2, and the right hand side will remain as it is 0 and 0. So I can if there is equal sign, so I can equate this equation equal to 0 and this equal to 0. So now first of all let's equate this first equation equal to 0. So I can bring this term minus term on the right hand side. So I can write in simple way 2 minus I under root of 12 times x1 equal to 4x2. So now we have find out the relation between these two variable x1 and x2. And now let's bring this 4 on this left hand side. So I can let's write it here. So I can say x2 equal to 2 minus I under root of 12 by 4 times x1. So now let's put the value of x2 here in this vector form. Let's call it v1. So I can write like this x1. Let's take it as it is. And here I can replace this x2 by this relation that we have got. Now here this x1 is common, so I can take it common from this vector. So I can write x1 multiplied with this vector. Here the value is 1 and here the value will be this. So now we have find out the first eigenvector. Here the value of x1 is maybe anything, but this here we have to find the either the vectors are complex or real, but here we are getting the complex. So regarding of this x1 value, here whatever maybe we are getting, this complex value will remain as it is. So now we can say the eigenvector is also complex because here in the vector form we are getting the complex term. So option D is the correct statement about the eigenvalue and eigenvector from these two steps. First step is there. Here we have find out the eigenvalue in this form, and the second step is this. We have find out the eigenvector in general way. So now option D is the correct one. Let's move to the question number 9. Okay, question 9 says a 3 cross 3 matrix has eigenvalue 1, 2 and 5 respectively. The determinant of a matrix. Okay, simple question. Just we have to use the property which is multiplication of all eigenvalue. Let's here we have 3 eigenvalue because the matrix is 3 cross 3 order. So I can say lambda 1, lambda 2 and lambda 3. If I am multiplying these three numbers, then I equate equal to the determinant of matrix. Let's call it M here in general way. So now they are asking about the determinant and here they are given the eigenvalue. So simply we have to multiply these three numbers. So 1 multiply with 2 multiply with 5 and equal to determinant of M. So I am getting 10 as determinant. Very simple question. It's only take 2 seconds to get answer. So the determinant is 10. Now let's move to the last question for this video. Okay, now let's solve question 10. So question 10 says for the matrix A we have values in terms of cos and sine. Here A is 2 cross 2. If that stand for the determinant and A transpose is the transpose of A, then the value of determinant of this A transpose time A. So first of all, to find the determinant, we can also decompose this term with the help of one property, determinant of A transpose time A. So simply we can decompose this term with the help of property of the determinant. So now I can equate this term equal to the individual determinant multiplied together. So I can write like this, determinant of A transpose, and I have to multiply it with the determinant of A. Simple word, the multiplication of determinant is just simply the multiplication of individual determinant of these two matrices. So now here from the property of determinant we can say the A transpose, determinant of A transpose, and it is exactly same as determinant of A, because here in this transpose operation we are just simply the interchanging row and column to find the transpose. We are not changing any value, so the determinant is the same. So here we can write also determinant of A multiply with determinant of A. So I can say I have to find the determinant and I have to square it to find the determinant of this A transpose time A. So first of all, let's find the determinant of matrix A here. Simply I have to multiply these two terms. So here cos multiply with cos, so cos square theta, and I have to subtract the multiplication of these two remaining entries. So minus, here I am getting minus sine square, so I will put plus here and sine square theta, and now here it is well-known identity of trigonometry eigenequate equal to unity. So now to find the determinant of this, I have to square this number. So again, squaring of 1, square of 1 is again 1. So simply we put 1 in this blank, and which is the determinant of this uh, 2 matrix multiplication after, sorry, determinant of this matrix after the multiplication of this A transpose and A, which has value of 1. And that's it, we have done. And thanks for watching this video and keep supporting this channel. Thank you very much.